Welcome to the world under the sea, where the moon jellyfish move through the water. Today, we are going to discover the science behind its movements. This is the moon jellyfish. Have you ever wondered why the moon jellyfish can move and maintain their shape at the same time? The secret lies in its hydrostatic skeleton. First, I will describe the structure of moon jellyfish. The structure of moon jellyfish has many structures, but today I will explain just some of them in line with the topic of hydrostatic skeleton. First, umbrella. Umbrella is thicker to the middle and thin toward the edge, and it is a reproductive organ. Second is ring of muscles. It is so important to the hydrostatic skeleton, and all jellyfish have a ring of muscle that encircle the bottom of the bell, which is the main component of the jellyfish anatomy. The bell is hollow and open-ended, allowing it to fill with water. The muscle allow the bell contract, squeezing out the water and propelling the jellyfish forward, upward, or downward, depending on the position of the bell at the time of compression. Third, subumbrella. Subumbrella responsible for the rhythmic contraction of the bell and composed of epitheliomuscular cells.
The fourth, nidocyte. Nidocytes are stinging cells that are small compartments with a stinger inside when an outside force triggers a stinger. The cell open, letting ocean water rush in. This causes the stinger to shoot out into what triggers the action. Once it there, we know is released. Then oral arm. This long appendage move capture prey to the animal mouth, which is usually found on the underside of the bell. These jelly inject food directly through opening in their oral arm. And the last, mesogear. Mesogear indicated that energy sufficient for extension could be stored by contraction of the mesogear.
After we understand the structure, in the next part, we will talk about the jellyfish movement. Moon jellyfish have hydrostatic skeletons, which are type of skeletal system that rely on the pressure of a fluid-filled cavity to provide support and structure. They have a fluid called mesogear between the outer and inner tissue. Water makes up most of the jellyfish body, controlling buoyancy and facilitating movement. This is a video of the movement of moon jellyfish.
The movement of moon jellyfish has a pattern called rhythmic pulsation of the bell. It means contracting and relaxing the muscle to move the bell forward, like when stripping the plastic of an umbrella off and then try to open or close it, which is make it similar to the movement of a moon jellyfish. The movement of the moon jellyfish has 4 steps. Step 1. The edge of the bell begins to contract. Step 2. Forcing water under their body into the egg umbrella. When it is full, it will expand the edge of the bell. Step 3. The jelly of moon jellyfish will contract the bell to create a stopping vortex. Step 4. The jellyfish will expel beyond the bell and start moving forward in the opposite direction of the water that was spread out. Here is an overview of the step of a jellyfish's movement. Next, let's follow us to discover the secrets behind its move by breaking it down into equation and the principle of physics.
We assume the moon jellyfish is a semicircle. As you can see on the left side, it is the figures of how moon jellyfish move. In this part, you can generate the model as you can see on the right side. This model will concern how much fluid pressure is produced inside the moon jellyfish and the force of forward directions of the moon jellyfish for possible comparison movement of the moon jellyfish. When the moon jellyfish contract their ring muscles, the volumes of their bell decreases. They squeeze the fluid-filled mesoglea. Then, the condensation increases pressure within the mesoglea. Due to the difference of the pressure inside the bell and surrounding water, The displacement of water from the sub-umbrella opening through the bell creates the forces that can push the jellyfish to move forward. From Newton's third law, the force of action is equal to the force of reaction, but it always has opposite directions. In the moon jellyfish, the fluid pressures of the action force always acts perpendicular to a given surface area. And in equilibrium, the reaction force of the fluid pressure is balanced by the muscle forces acting along the two edges. So, we can determine that the fluid pressure produced inside the moon jellyfish times the surface areas of the moon jellyfish is equal to 2 times the force generated by the contractions of the bell times the circumference of the moon jellyfish. Next, we substitute the surface areas of the moon jellyfish equal to pi times the radius of the moon jellyfish squared divided by 2, and substitute the circumference of the moon jellyfish is equal to pi times the radius of the moon jellyfish in the equation. These allow you to determine the fluid pressure produced inside the moon jellyfish based on the force generated by the contractions of the bell and the radius of the moon jellyfish from this equation. After we have some information on fluid pressures from previous step of calculations, the force of forward directions of the moon jellyfish can be defined from multiplying fluid pressures by pi and the radius of the moon jellyfish square and then divided by 2. This equation represents the force generated by the fluid pressure inside the moon jellyfish acting on its bell, which is the movement forward through water. Next, let's see the calculation. For the calculation, we will compare the fluid pressure produced inside the moon jellyfish and the force of the forward directions of the moon jellyfish using the radius equal to 3 cm and 4 cm respectively. Using an area of the ring muscle equal to 1.5 times 10 raised to the power of negative 3 square centimeters and a maximum force generated by muscle equal to 7 times 10 raised to the power of 6 Ds per square centimeter. And we will note that 1 D per square centimeter is equal to 7.5 times 10 raised to the power of negative 4 torr. As you can see here is the calculation that due to radius equal to 3 centimeters. From the formula of 4 times S times AM and divided by R. If you substitute the value in this formula, you will got 1.4 times 10 raised to the power of 4 D per square centimeters. And you can change the unit to the torr unit. So you can get the P equal to 10.5 torr. Next, you find FF equal to P times pi R squared divided by 2. If you substitute the value in this formula, you will got FF equal to 1.978 times 10 raised to the power of 5 D. Next is the calculations of R equal 4 centimeters. When we substitute the values in the formula P equal to 4 times S times AM and divided by R, you will got 1.05 times 10 raised to the power of 14 per square centimeters. And you change unit, so you will got 7.875 torr. And you find FF from P times pi R squared divided by 2. When you substitute the values in this formula, you will got FF equal to 2.64 times 10 raised to the power of 15. Then we use this calculation to compare in the next part.
Let's discuss and conclude all of the contents. For moon jellyfish, the mesoclade and ring muscle are the important structure that form a hydrostatic skeleton that supports structure and flexibility, allowing jellyfish to move, swim, and maintain their shape in the water. In our calculation, we use 2 different radius of moon jellyfish for comparison. We can see that the higher radius lead to an increase in the force of forward directions. After the contraction of ring muscle, the relaxation of ring muscle will occur, and this allows the bell to expand and return to their normal shape. And this cycle of contraction and relaxation will help jellyfish to continue moving. And that's it, the secrets of the moon jellyfish movement, explained with equation, science, and the principle of physics, help us to understand the movement of moon jellyfish under the water.
Thank you for joining us on this journey, where we make simple to discover the science behind the moon jellyfish movements.